Hi and welcome to this video on evaluation metrics for classification models. I am Raghavendra, an expert in AI, ML and data engineering. By the end of this video, you will be able to learn to interpret the confusion matrix, explain different performance metrics for classification problems, learn to choose the appropriate threshold value of the predicted probabilities for making predictions, understand class imbalance and the need for different performance measures. Here are the different evaluation metrics for classification models: accuracy, true positive rate or recall or sensitivity, specificity, false positive rate, precision, F1 score and ROC AUC, which is nothing but the receiver operating characteristic area under the curve. These performance metrics can be derived from the confusion matrix. Now, let's take a look at the confusion matrix and try to understand it in more detail. A confusion matrix summarizes the performance of a classification problem. Suppose the target column has two categories, then the confusion matrix will be a 2 by 2 matrix. In general, if the target column has n categories, then the confusion matrix will be n by n matrix. Here is a confusion matrix of a classification problem with 192 observations in the test set to predict whether a person has a disease or not. In general, a confusion matrix is a comparison between the actual values and the predicted values of a model. Here, the target column has two categories with values 0 and 1. 0 or no indicates a person does not have the disease. 1 or yes indicate the person has the disease. The columns of the confusion matrix represent the predicted values and the rows represent the actual values. From the confusion matrix, the total actual no's in the test set is 126. The total actual yeses or the positive class is 66. The total predicted no's is 171 and the total predicted yes or the positive class is 21. Now, let's take a look at the four quadrants of the confusion matrix in more detail. Suppose there are people waiting for an examination from a doctor for a disease. The doctor uses the outcome of a machine learning model to conclude if the patient has a disease or not. The model predicts the patient has the disease and actually the patient has the disease, and this is called as true positive. If the model predicts the patient having no disease and actually the patient has no disease, that is called as true negative. The model predicts the patient to have a disease and actually the patient has no disease. This is called as false positive or type 1 error. The model is predicted to have no disease and actually the patient has a disease. This is called as false negative or type 2 error. In our example of the confusion matrix, we have true negative as 120, we have true positive as 15, false positive as 6 and false negative as 51. From the confusion matrix, the total correct classification is 135, which is nothing but the sum of the principal diagonal elements, that is 120 plus 15. The total misclassifications of our model is 57, which is nothing but the sum of the secondary diagonal elements of the confusion matrix. Now, let's move on and understand what is accuracy. From the confusion matrix, the proportion of the observations which were correctly predicted, that is, the true predictions upon the total number of observations n is called as accuracy, is given by true negative plus true positive divided by the total number of observations. In our confusion matrix example, we have accuracy as 120 plus 15 divided by 192, which is nothing but 0.703. Next, let's move on to understanding what is true positive rate or sensitivity or recall. Out of all the positive classes, true positive rate measures how many instances were predicted correctly. The proportion of the patients who have been correctly predicted to have the disease upon the total number of patients who actually have the disease is the true positive rate or sensitivity or recall. It's given by true positive divided by true positive plus false negative. From our confusion matrix, sensitivity is 15 divided by 15 plus 51, which is equal to 0.2272. Next is specificity. Out of all the negative classes, how many instances were predicted correctly? The proportion of the patients who were correctly predicted not to have a disease, that's true negative upon the total number of patients who actually do not have the disease, which is the sum of true negative and false positive. Specificity is given by true negative divided by true negative plus false positive. In our example, specificity is given by 120 divided by 120 plus 6, which is nothing but 0.95. Now, let's move on to understand what is the false positive rate. Out of all the negative classes, we are trying to find out how many instances were predicted incorrectly. It's a measure of how many incorrect predictions have been made out of all the negative classes. It's also called as inverted specificity. The proportion of the patients who were incorrectly predicted as having the disease upon the total number of patients who do not have the disease. That is, false positive rate is given by false positive divided by true negative plus false positive. From our confusion matrix, the false positive rate is 6 divided by 120 plus 6, which is 0.047. Precision is defined as among all the positive predictions, how many were predicted correctly. Among all the positive predictions, we are figuring out how many were predicted correctly by the model. The proportion of the patients who were correctly predicted to have the disease upon the total number of patients who were predicted to have the disease, that is, true positive divided by true positive plus false positive gives us the precision. From our confusion matrix, precision is 15 divided by 15 plus 6, which is equal to 0.714. The next performance measure is the F1 score, which is the harmonic mean between the precision and recall. A higher value of the F1 score indicates the model has a very minimal misclassification rate. F1 score is given by 2 times the precision multiplied by recall divided by precision plus recall. From our confusion matrix, we had obtained that precision is 0.714, recall as 0.227, and F1 score comes to 0.344. Now let's understand the next performance metric, which is the ROC curve and the ROC AUC. ROC curve is the receiver operating characteristic curve, is a probability curve that plots FPR versus TPR values for various threshold values. By default, predictions are based on the predicted probabilities with a default threshold value of 0.5. If the predicted probability is greater than or equal to 0.5, then the predicted class is class 1 or the positive class. If the predicted probability is less than 0.5, then the predicted class is class 0 or the negative class. The true positive and false positive rates vary for different values of the threshold of the probabilities. The area under the resulting curve of the receiver operating characteristic curve is a measure of the performance of a classification model. Higher the area under the curve value, better is the performance of the model in making correct predictions. And here is the graph between the false positive rate and the true positive rate. The ideal value of AUC is a value close to 1. Higher the AUC indicate higher true positive rate and lower false positive rate values. Higher TPR indicate the high value on the y-axis, which indicate higher true positives and lower false negatives. Lower FPR indicates lower value on the x-axis, which indicates lower false positives and higher true negatives. Lower false negatives and lower false positives indicate an ideal scenario with the least minimal misclassification. By varying the threshold of the predicted probabilities, we can check if it's possible to minimize the misclassifications and in turn increasing the correct predictions. The threshold value of 0.5 is not always idealistic. The AUC of the ROC measures if the model can make correct predictions by changing this threshold value. The ROC curve shown is for an ideal scenario with no misclassifications, and hence the area under the curve is equal to 1. It's desirable for models to achieve area under the curve value very close to 1. In practice, there exists a trade-off between false negatives and false positives. False negatives and false positives are our misclassifications. So, if you try to increase your false negatives, false positives decreases, or if you try to increase false positives, your false negative decreases. It's impractical to achieve zero misclassifications. Hence, we can choose the appropriate threshold from our ROC curve to minimize either the false negatives or the false positives. Now, let's understand this through a scenario. Here is a confusion matrix for a classification model for predicting whether a person has been infected by COVID or not. There are 1,000 test observations with an accuracy of 96%. Can we conclude this as the best model which results in such high accuracy? The answer is no, we cannot. Let's try to understand this in more detail. Here, there are 40 misclassifications with 5 false positives and 35 false negatives. 35 false negatives can be disastrous where people are incorrectly tested negative. These people are likely to spread the disease to a larger population. In this scenario, the objective is to achieve a minimum false negative and a higher true positive so that the spread of the disease can be contained. From the ROC curve, an appropriate threshold is chosen, which results in a higher true positive, which in turn minimizes false negative. Let's now take another scenario. We have a confusion matrix for a classification model based on biometric fingerprints for predicting whether a person is authorized to enter the organization or not. There are 1,000 test observations with an accuracy of 99%. Can we conclude this as the best model which results in such high accuracy? The answer is no, we cannot. Let's understand this in more detail. Here there are 10 misclassifications with 8 false positives and 2 false negatives. 8 false positives means 8 people have unauthorized access to the organization, which is a major security breach. Here the objective is to achieve a very minimal false positives so that no unauthorized person is allowed entry to the organization. 8 false positives are in fact very high number that should be reduced. From the ROC curve, an appropriate threshold is chosen which results in minimal false positives. Higher accuracy alone does not mean that we have the best model in place. A detailed analysis of the confusion matrix is to be carried out to understand the strengths and weaknesses of the model. Now let's understand what is class imbalance, which is one of the leading problems in a typical binary class classification problem. Most of the datasets for classification problems do not have an equal proportion of the categories in the target column. There will be an overrepresentation of either of the classes, resulting in the class imbalance of the target column. From the confusion matrix, it is evident that class 0 representation is 98.5% and class 1 representation is 1.5%. In such a scenario, the model will be biased towards the majority class, and accuracy alone cannot measure the performance of the model. Hence, other performance measures like precision, recall and other measures are to be looked out to measure the strength of the model. Now let's summarize the key takeaways from this video. Accuracy is the proportion of the test observations correctly classified to the total number of observations. True positive rate is a measure of how many instances were predicted correctly among all the actual positive classes. Precision is a measure of how often a positive class is correctly predicted among all the positive predictions. F1 score is the harmonic mean between precision and recall. The ROC curve is a probabilistic curve between the false positive rate and true positive rates for the various threshold value. Thank you for watching this video.